jokes to tell. It's too early in the morning. I've been here about 10 times, and every time I come, I fall off this side right here. I'm telling you, also, add a little thing right here that allows you to walk and talk and right here. I've lost that battle. There we go. Okay, so we're going to be doing optimization this morning, and we're going to be doing theories. This is a theory talk for theory people. I guess I can tell the anecdote that I went to China in December, and I gave something like this talk, a bunch of kind of theory stuff to big audiences, because in China nowadays machine learning is really, really popular. So like literally audiences of 3,000 people. And at the end of it, all these kind of theoretical concepts, you know, they kind of nodded politely, but everyone raised their hand and said, well, what do you think about deep learning? So I think I'll start this talk by saying, here's what I think about deep learning. It's important to be empirical and try things out and do it at scale and learn phenomena. And so I was around in the 80s when that was all everyone did. That was the early machine learning. Very, very empirical. And of course there was this kind of covering number of people that, you know, proved some semi-relevant theorems, but it was mostly empirical. And I think that's really great, but you know, in my own career, I just wanted to kind of do something a little more mathematical and turn over to the next generation, so something a little more mathematical, and so slowly help to move the field in that direction. And it, you know, many of us have done that, and it really worked, but now the field has gone way back, the pendulum has swung back, it's extremely empirical again. And so when you talk about machine learning in the outside world, that's what you need, is all this empirical neural net stuff. And again, that's great, I think it's changed the world. But for the young people in the room, there's a whole other world of theory. And I think, so I'm going to just go ahead and move to my second slide here. Here's one way of trying to get into these issues, is that if you really look at the amount of platforms we're working on, they're distributed, they're parallel, they're asynchronous, they're complicated in all kinds of ways. And so kind of classical results for single processor, you know, synchronous, et cetera, break down when you get into this setting. So there's all kinds of brand new theory problems, and they really matter, because if you don't do this kind of stuff right, worry about communication, worry about asynchrony, you're going to get algorithms that are wrong and surprisingly slow and will break in various ways. So there's just all kinds of really good challenges here. So this is kind of a part, this is the optimization side. Of course, there's also the kind of the statistics side of analyzing things. And so today just focus on optimization, but of course there's all those other sides as well. So I decided to kind of pick a few themes that tell little stories. My group is now really focused on optimization, because I do think that it's an era where you can really do fundamental theory. If you look around for lower bounds in statistics and computer science, there's not that many of them out there. Computer science doesn't have very many. Statistics has more, but they're kind of done in a very classical setting. So there's a lot of opportunity to kind of think about lower bounds when you think about optimization, because optimization has these oracle lower bounds, and there's kind of a classical set of them that are intriguing and interesting, but also very limited. So I think there's a lot of room open now to kind of think about lower bounds. So there's a little bit of that in this talk, and that's what a lot of my group is interested in these days. So here's an outline of just some of the topics I picked. A couple of my co-authors are in the room who may be able to help me. The first one is about going to continuous time. So I think this is actually critical. Almost all of our theory work has been done in discrete time and algorithmic time. And you don't see a lot of the phenomena in a clean, crisp way in discrete time. You can see them much more cleanly in continuous time. So I'm going to focus on that a bit. That's just kind of getting started, that line of research. Particularly the word symplectic is important. There's a lot to do there. A little bit about saddle points, because if you do want to get out of the convex world, you have to think about saddle points, and you have to think about how to avoid them efficiently in high dimensions. Then Liwa is in the room. I've worked with Liwa on something called stochastically controlled stochastic gradients, and trying to use stochastic gradients but remain efficient. That's kind of a line of research that's been going on for about 5 years now, and I'm contribute to that. And then I may or may not get to some of these other things. The last one, I do kind of, if I leave, hopefully leave time for it. This is less theory-oriented, but talking about some collaborations with systems people, and I think this is really a fantastic venue for collaboration. Machine learning has often been thought of as an AI kind of collaboration, stat AI. But stat systems is really a I've been doing that for about 10 years now, and I want to report on kind of some of our latest work there. So let me start with this variational Hamiltonian symplectic work. This is work largely with Andre Levisona and Aisha Wilson, who are students here, or what were students here. Andre's moved on to Wisconsin. And then Mike Betancourt has joined us in this last little wave of this activity as we started to think about symplectic integration. Okay, so this is an attempt to talk about Nesterov acceleration in a different way. Try to get some new, so I'm clipped at the top, I guess that's like. All right, so let's just set up some notation here. This part of the talk is going to be convex optimization, unconstrained. So all of us know what our friend classical gradient descent is. This is going to be non-stochastic, this part of the talk. We're just going to talk about gradients and gradient flow. So as presumably you all know, in this general setting, just smooth but not strongly convex, we get convergence rates of the form 1 over k. That means after I've seen k gradients, my error is within 1 over k of the optimum. That was known, I don't know, for 300 years or something, roughly, but it came out as a general theory just in the last sort of 40 years. And then at some point someone asked, are there lower bounds that one can talk about? Is this the best you can do? Well, what do you mean the best you can do? A convex function, there's a single optimum somehow. If you just look at the thing, you could find it. If you were allowed to have a higher Taylor expansion, you could just solve for it, and so on. So the Nemirovsky-Yudin perspective, which emerged in the sort of 70s to 80s, and others, and mostly the Russian school, defined the notion of an oracle, and there are many different kinds of oracles, but one of them was that you can look only at gradients. You're allowed to access the function value of the gradient anywhere you want, and your algorithm is constrained in some way. So maybe it can only take its new step in it can access gradients in the span of all the gradients you've seen before. Some constraint on the computational power of this. So it's not a kind of classical computer science constraint. It's not kind of the Turian spirit. Right? It's its own thing. And so under constraints like that, you could get lower bounds, and they turned out to be 1 over k squared. They were faster than gradient descent. And this is kind of a surprise to people in that era. I vaguely remember some of this. Gradient descent seemed optimal if you're just allowed to only look at gradients and have a fairly strong constraint. You can't just look at a gradient everywhere. It is taking the steepest descent direction, and even if we give ourselves an oracle to tell us how far to move, it's still suboptimal. So it was a surprise that there was an algorithm this simple that came along that had a faster rate than gradient descent. This is Nesterov acceleration, and one of the many ways to express it. So it has now 2 sequences, not just one. And one of the sequences, the y value, basically does a gradient step using the x values, and then the next x value is a convex combination of the last 2 y values. So many people stared at this and tried to think about their own perspective on it and explain it. There are many kind of interesting explanations of it. One thing that I think many of us have noticed looking at this at some point is that this is important here. There's a yk plus 1 here. So this kind of looks like a classical kind of explicit step. If you think about integration, this looks like an implicit step. And if you know anything about the combination of explicit and implicit, that's like the leapfrog integrator. Oops, I forgot to put this on. I told you I'd do it. All right. Start again. I can start again. Sorry to all you out there. Now I've just woken up anyway, so it's going to be a better talk from here on. Okay, so there's Nesterov acceleration and leapfrog integrator. It looks kind of like a leapfrog integrator if you know anything about integration. Now, most people do optimization don't think about integration very much. So why in the world would this be integration? Integration of what? Okay, so that's part of the purpose of the first part of the talk, to relate optimization and integration. So in fact, if you're Bayesian frequentists, that's kind of nice to know that those things can be more closely linked, because the frequentists mostly do optimization kind of things, and the Bayesian mostly do integration, and they're actually more close than you might think. That's one of the points of this part of the talk. Okay, so just again, the kind of history was, there was all of these gradient methods, including things like mirror descent, cubic regularized Newton, and so on, that were being studied. Rates were being achieved for those, and then oracle models were set up. And the oracle models were typically had a better rate than the gradient-based or the higher gradient-based methods. And so you could accelerate sort of all these things. And so there was a whole line of research, there is to this day, of accelerating these things. Oops. And how did you do this? Well, there wasn't really kind of just a generative mechanism for taking the Nesterov idea and just sort of applying it to an algorithm and accelerating it. Mostly as you kind of look at the algebra and you learn Nesterov's style, and you kind of do similar algebra in problem after problem. That's what people did. And derivations are sort of a few pages typically. There's kind of an estimate sequence technique, but it's really more about analysis than about generating algorithms. But nonetheless, this has gone on, and there's just very many important real-world applications of this acceleration idea. Interestingly, intriguingly, these are not descent methods. So they will go down, and then they will come back up. That seems suboptimal, but it's not, counterintuitively. And sort of the intuition is that if you're going to kind of go really fast down the road, you got to kind of take the curves pretty quick. And so a little sloshing is going to be needed and allowed and in fact needed. Okay, so let's move into the continuous time world right away. So gradient descent is the discretization of what's called gradient flow in mathematics. There are huge textbooks on gradient flow. It's an old area, still active to this day. So it's a differential equation. There's no step size. I just write down the differential equation. And if you want to solve it on a computer, you have to integrate it with an integrator. So you could use something like Runge-Kutta or whatever, and you'll start to introduce things like step sizes. But the differential equation has no notion of a step size. So there was a very nice paper that we saw, came out in 2014 from Stanford, Sue, Boyd, and Candice, where they took Nesterov acceleration, those two equations I showed you, and they took the step size analytically to 0 and took those difference equations and turned them into a differential equation. And here's what popped out. It was a second order differential equation. It was non-homogeneous. There was an interesting factor of 3 there. And that is an ODE that you cannot solve, but you can numerically solve. There's Bessel functions that allow you to sort of understand this solution. And the Bessel functions have oscillations, so they could study these oscillations and sort of understand them a little bit from the point of view of kind of applied ODE research. So that was pretty interesting. But looking at that, sort of, you ask the question, why that differential equation? What's special about that? Why would you have ever written that down? Or what's the principle that delivered it? All right. In particular, if you're trying to think about this notion of achieving an oracle rate, the oracle rate is somehow the best you can do. So there must be a principle that says it's best for some particular algorithm is best for some reason. So what we're really asking for in this field, I think, is what's the best way to optimize? What's the optimal way to optimize? Okay? So I don't think we've ever really stated that as clear as we should, but that's really what we're asking for. So if you write down a way to optimize in continuous time, you have to say kind of why that's best. It's not just enough to write down a differential equation, and in discrete time, similar story. You've got to write down a difference equation for some reason. Okay, so that got us started thinking about that. Is there a deeper generative mechanism that generates this? And then maybe some other accelerated looking ODEs for other areas that are discretized in some way. So we're going to start by talking about a variational approach to acceleration. And then the key of this is actually not so much this. This is in some sense not that hard. The key is actually the discretization. And if you know any real physics about how you take differential equations of the cosmos or proteins, those are differential equations. How you discretize is the key. Right? If you discretize them the wrong way, you lose things like conservation of momentum, conservation of energy. You don't do the right physics. You have to discretize them the right way to actually do real science. So I think that our field I think it'll be useful for us to take on that point of view. Okay, so I'm just going to jump right to it. So what does variational mean? So first of all, it's a whole area of mathematics. And what it really means is that you take some problem of some kind, algebraic or geometric or whatever, and turn it into an optimization problem. That's what variational really means. So eigenvalues, right? How do you define an eigenvalue? Well, ax equals lambda x. Well, that's an algebraic definition. There's another way, which is write down a Rayleigh coefficient, and you optimize. You've turned it into an optimization problem. The eigenvalue is the maximum over a ratio. And there's lots of other problems where you took something that didn't look like optimization, you turn it into an optimization problem. Why? Well, there's now a whole slew of numerical methods, analytical techniques that apply, but most importantly, you can start to approximate now. You can say, well, the original solution can be written as this optimization problem. I can perturb the optimization problem, and maybe topologically I haven't perturbed the solution too much, and the perturbed problem is easier to solve. Okay, so that's the whole spirit of variational ideas. And finite element methods is a variational methodology and so on. All right, so the word, of course, comes from calculus of variations, and the first user of that was Lagrange. And Lagrange looked at the differential equations of Newtonian mechanics, like F equals ma, and said, is there a generative principle for those differential equations? Newton invented them, but is there a better underlying principle? And so he says, yeah, there was. There's this object called a Lagrangian, which instead of writing out a differential equation, I write down something that I integrate. Okay, so the flip side of the duality of calculus. And now you optimize that integral. And that's the Lagrangian perspective on dynamics. And then Hamilton kind of refined it. And then it turned into the main tool in the last century for physics, not the Newtonian point of view. All right, so here's going to be our Lagrangian. A Lagrangian is just a function of paths. So x is a continuous time path, x dot is its derivative, and these are going to be non-homogeneous, so I put time in there. And the first term here is a Bregman divergence, and the second term is the function we're trying to optimize. And all those little e's are just scaling functions to give us a variety of algorithms, kind of give us some degrees of freedom. Okay, so here's our friend the Bregman divergence right here. You all know what it is. If I want to measure the distance between x and y, I could do that with an auxiliary function h, take the discrepancy between the linear approximation at x and the actual value at y. That distance there is the distance between x and y on this axis measured with this auxiliary function. That is the Bregman divergence. If h is quadratic, this is just another way of defining Euclidean distance between x and y. All right, so what we're doing here is putting Bregman divergence in as this first term of this thing to be optimized. Okay, so I'll tell you how I optimize it in a minute. It's interesting in Bregman divergence. It takes where you are right now, and it takes where you are plus a little bit of velocity. All right, so it's kind of like a stretching in some direction. It's kind of an energy term. All right. Again, these are just time scalings. Forget about that. This is the key part: x plus delta x. All right. So think of that kind of like a kinetic energy, and think of this as a potential energy. In fact, forgetting that, this is just kind of the function you're trying to go downhill on, so it should be your potential. You want it to go down. If you actually plug in h being quadratic, suppose h is quadratic, then that Bregman divergence simplified is exactly the kinetic energy. So if you're a physicist, you say, okay, that really looks like a classical Lagrangian from physics, kinetic energy minus a potential energy. All right, now we have 3 of these time scaling functions that have been put in just to give maximal flexibility to this Lagrangian. But if you want to get optimal rates from this thing, it turns out there's only really 1 degree of freedom. The alphas, betas, and gammas are related by what we call the ideal scaling conditions. So if you set alpha, that's going to determine beta and gamma. And if you set beta, that's going to determine alpha and gamma as well. So I'll get into that a little bit more, but let's just assume there's 1 degree of freedom. Okay, here's our Bregman Lagrangian. Now, what do you do with Lagrangians? Well, you do calculus of variations. So you stick the Lagrangian as a function of paths into an integral. You integrate this as a function of time, and then you minimize over paths. So you pick the path which minimizes what's called the action in physics, the Lagrangian. All right, so we've now got ourselves an optimization problem. We can solve this in many different ways, maybe numerically, whatever, right? But the first thing to do is to get necessary and sufficient conditions for an optimum, or at least sufficient conditions. So you get that by, in essence, taking the partial derivatives and setting them all to 0. That's what you do in discrete spaces. In continuous spaces, that's called the Euler-Lagrange equations, and it's just a differential equation. Okay, so it sort of takes a bunch of partial derivatives of L with respect to its 2 arguments. And this is now a function of time. You take its total time derivative, and you can easily do that. You can just hit this thing with derivatives, and out it's going to pop just an ODE, a differential equation. All right, so let's just do that. Here is the differential equation that results. So let's call that the master ODE. I claim this is going to generate essentially all known accelerated gradient methods in continuous time. All right, so this master is worth looking at for a moment. It's second order. It is non-homogeneous. It's got some geometry here. This H is going to give us different geometries. If we're working on manifolds, we would get different H's. And then we have, lo and behold, the gradient of the function we want to go downhill on. So it looks like kind of a damped oscillator sort of setting for minimizing F, which that's pretty natural. Okay, so let's now try to get some more insight into this. First of all, we can get a rate in continuous time. If you were to solve this thing in continuous time, you would approach the optimum of f at a certain rate in continuous time. And then here we get a little sense that we're on the right path here with this methodology, because getting the rate is actually 1-line proof. Yeah?
The variational problem doesn't depend on the endpoints of your curve?
It does. The one endpoint is going to be the optimum. The other endpoint is an arbitrary starting point, and so you get the same. Yes, there'll be there's an initial. It's an initial condition problem. It's not a 2-point boundary problem.
And the And the Hessian is evaluated at a different point and then xt.
Yep, that's right. It's evaluated at this sort of forward point, but it's still a well-defined differential equation, and that's really critical to get this acceleration notion. If you had evaluated just at xt, it wouldn't have accelerated. Yeah.
So is h like given to you as part of the constraints of the problem, or is
No.
h something you're choosing?
It's you're a designer of the algorithm. You choose h. So I maybe tell you what manifold I'm on. Let's say I'm on the space of all semi-definite matrices. Then you would choose an h which is fitted to that.
Because you call this a Lagrangian, so I kind of want to attach the first term somehow as like the lambda times the constraints of the problem. But you're saying that's not how you should think about that.
Well, I like to think about it as a separate degree of freedom as the designer can use. I don't have to use the natural geometry. I might want to use a different one for my own purposes. I mean, one way to think about it is just forget the geometry. It's just that write down a lot of h's and try them out. You'll get a whole span of algorithms, and some of them, can be used for different problems. Okay, so there's a one-line proof of convergence here of this thing. So here's the convergence rate. It turns out to be order e to the minus beta t. So that beta t that you chose determines the convergence rate. And here's the proof. You just simply write down a Lyapunov function that uses this Bregman divergence. All right, take the first derivative of this, the time derivative of this Lyapunov function. Here it is right here. And ask that the Lyapunov function be less than or equal to 0. The condition that achieves that is exactly this rate here. Okay, so that suggests that this is a kind of a useful way to actually just kind of collect the dynamics of these optimization problems in one formalism. And Bregman divergence plays a key role. All right, but that's not the main story. The main story is something else. So first of all, this is wildly ambitious. This suggests that we're able to get exponentially fast algorithms. We know that we're not able to get that in general. We're able to get these 1 over k squared, polynomial kinds of rates. We can get exponential rates in some settings, but very strong assumptions are needed. So what gives here? So let's assume that we know already that we can't get exponential rates. So let's be less ambitious and let's explore what happens when we set beta to be logarithm of t. So the logarithm will kill the exponential, and let's give ourselves an extra degree of freedom. Let's call it p log t. So I can get t squared, 1 over t squared, 1 over t, even higher values of polynomials. Okay, so let's do that. Let's set beta equal to p log t. This will turn into 1 over t to the p. Okay, and then alpha and gamma are determined once I picked that. So now the convergence rate for that choice, if we can achieve it, we're just going to write down a differential equation. We don't know we can solve it yet. Will give us this rate of convergence. Okay, so we'll get gradient flow t when p is equal to 1. And we might hopefully get a span of other interesting algorithms in continuous time. All right, so if you plug that into our master differential equation, you get this differential equation now. Still has some geometry. And now this is starting to look a little simpler. And in particular, when p is equal to 2, we get that mysterious 3 there from Sue, Boyd, and Candace. Yeah?
What is the barrier for actually getting the exponential rate?
We know that in these smooth convex problems, we're not going to get it. All right? If we have uniform convexity, we're going to be able to achieve exponential. Now, so the barrier in continuous time does not exist. Okay? In continuous time, you can achieve the exponential rate, but in continuous time, the notion of rate is actually not very deep. It just means I've changed the clock. So if you're using a certain clock, and I reparameterize the clock with a one-to-one function, I can go as fast as I want. All right? And in some sense, the fact that acceleration is not a mystery in continuous time is what allows us to explain it. Okay? It's just a change of clock. The mystery then is solved by when you go back into discrete time, something will break. The exponential rates in continuous time are not achievable in discrete time, whereas the other rates are achievable in discrete time. So it's the theory of discretization where the acceleration thing starts to get explained. Okay, so there's our differential equation. And if we start now setting p particular values, I already alluded to p equals 2. If p equals 2, we get this Sue, Boyd, and Candace. We've recovered that. We also can get the mirror version of this as well, which has this convergence rate when p is equal to 2 if we use a different h. Okay, so that's for p equals 2, but we are perfectly happy to also take higher values of p as well, and we can get other kinds of rates. So, for example, cubic regularized Newton can be gotten out of this framework, and then higher values of p are interesting as well. All right, so now if you start looking at the differential equations for different values of p, if you start looking at differential equations for different values of p, let's write them down and see what mathematical structure is emerging here. So here's p equals 2, where we get this convergence rate. So there's the differential equation. Here's p equals 3. Let's just try it out. We get this convergence rate in continuous time, and here's the differential equation. And you don't have to be an expert in differential equations to look at this and see some similarities. They're really the same differential equation, just like 3 is changed to 4, 4 is changed to 9, 2 is changed to 3. All right? And so what's happening here, and this is the first part it starts to get interesting, is that this Lagrangian has a mathematical property which is known as covariance, which means is that as I change p, I'm actually getting the exact same path in continuous time. The path is not changing. What's changing is my rate of moving along the path. All right, so for p small, I move at a slow rate. When I turn up p, all I do is take the same path and move at a faster rate in continuous time. All right, and then on the next slide, there's a proof of covariance. It's just that it's invariant to reparameterization. So this is true of this class of Lagrangians. It's not true of gradient flow. If you reparameterize the clock in gradient flow, you obtain a different path. All right, so that suggests there is an optimal way to optimize in a sense. It's actually the path, which is something interesting about the path. And the speed you move along it is not the important part. Yeah.
So I mean, the accelerated path obviously is a different path than the gradient flow path.
That's right. It's a different flow than the gradient path.
So
Yeah.
like 2 slides ago, when you said you had all these alpha t's, beta t's, and then
Yeah.
you set all of them according to a single parameter p.
Yeah.
You set them in a special way, presumably.
That's right. So this is a particular class of algorithms that are kind of on the Nesterov-Nemirovsky spectrum. They're all the gradient-based methods.
Can I add another parameter there and get something that goes from gradient flow to the acceleration, and then figure out what the optimal
All right.
acceleration is?
Wait, great question. Wait, at the end of the talk, we're going to talk about that. Okay, because that is really the key. That momentum and gradient flow both belong in the same algorithm. Okay, to get the I think the ultimate story. Let's just focus on the momentum kind of flows for now, and we know gradient flow exists, and we'll talk about putting the two together. So here's the proof that this is a covariant operator. You just simply reparameterize time. If I go from t to tau t, I've just changed my notion of the clock, and I plug that into my master differential equation. I can recover that by simply a change of redefining the parameters, getting alpha tiddles and twiddles and beta twiddles and so on. Okay, so under this situation, these certain set of assumptions, we have an optimal way to optimize. There is a particular path, and acceleration is just changing the speed at which you move along it. Okay, so in that sense, the mystery has gone away in continuous time. It's actually trivial. It's not even a mystery at all. All right, but now the whole key becomes how do we discretize to get back from just continuous time to discrete time, and stay stable and still retain the fast rate in discrete time. All right, so let's try to discretize those differential equations. Well, first of all, they're second order, and so the standard way of discretizing is to turn them into 2 first order equations to which you apply, say, Runge-Kutta or Euler. Okay, so here are the 2 first order equations. At this part of the talk, there's a bunch of symbols that just come into the discretization. I don't really want to go through all the details. I just want to give you a flavor. There's nothing particularly hard happening here. It's just things like Euler discretization applied to these 2 first order differential equations. When you do that, out pops this particular algorithm right here. This is an algorithm. You can put it on the computer. It's Euler discretization of that underlying differential equation. But it's not stable. All right, so here it is. Just run it on the computer. It sort of seems like it's doing pretty well. It starts to arrive down here, and then it shoots off to infinity. All right, here it is on one dimension shooting off to infinity. So you would never want to put this on your computer and actually propose this as an algorithm. Moreover, it loses the fast rate. Okay, so this was a bad discretization, bad idea. All right, so you could turn to other things like just Runge-Kutta or look at stiff differential equation methods and all that, and they also don't work. They aren't stable and they lose the fast rate. All right, so at this point it became a bit of a conundrum. How do you discretize these differential equations? They're kind of not classically studied. There's not a literature on them, seemingly. Okay, so there's now 2 paths to our little research project here. One of them is that we did discover a discretization method by taking Nesterov's equations and looking at them and reverse engineering, thinking them as a discretization methodology for differential equations. That's not how Nesterov thought about them, but you can look at them and think of them that way and turn them into a discretization of these differential equations, taking his style and applying them. And when you do, you get an algorithm that we can now prove is stable, and we can prove that it achieves the fast rate. And it's a very Nesterov-looking algorithm, although it's not exactly Nesterov. So I'll show you that result All right, but I think better way to think about that, and this is ongoing research, is to remember that there's this notion of symplectic integration. So I remember this back when I was at MIT. I was taking a class on differential geometry, and they talked at some point about discretizing differential equations, and they gave the usual long list that I just alluded to, and they said, well, that's what people really do in practice. And someone said, what do they do in practice? They said, well, they do symplectic integration. And so let me just say what that is before I get into it. If you go to a chemist or a physicist who's simulating the cosmos or simulating a protein and ask them, how do you discretize your differential equations? And they say, well, we use symplectic integration, of course. And people spend their whole careers doing symplectic integrators. And symplectic is a geometric term, and what's happening here is suppose I do a Hamiltonian and I'm doing something, the cosmos, so I know that energy is conserved and momentum is conserved. So I'm on cycles. The differential equation gives me cycles. So along that cycle, say energy is being conserved. All right, so if I were to try to get that cycle by discretizing, I'm going to get a little procedure that hops along. And of course, it won't be exactly lying on the cycle. Right, and I'll have steps. But I could ask the interesting question about, is there a discretization that, even though it's approximate, exactly conserves energy or exactly conserves momentum? So even though it's a numerical method now and I'm getting an approximation, at least the physics is still there. I haven't lost. Because otherwise, if I simulate the cosmos from the Big Bang till now, I'm going to be bleeding away energy and momentum. I'm just not doing the right physics. Okay? It's not even approximate in a reasonable sense. All right? So this was a problem in the 1800s, and Jacobi of Jacobians and Hamilton of Hamiltonians figured out a whole theory for it, and it's called symplectic integration. So they figured out a way to conserve quantities like energy and momentum. And so the right way to think about it is you go into phase space. You take x and you do Differential conjugate of the velocity, and you get the momentum. And now you get x comma p. And in that phase space, the differential equations have a certain form. And along the orbits, you don't want to just look at the vector along the orbits. You want to look at a little triple of vectors. You want to look at a little local Jacobian. And that Jacobian, as you flow along, should be conserved in volume. And there's a differential geometry version of this where you're taking exterior forms and you're conserving them as you move along this. So it has kind of a stiffness property, that there's a little local volume conservation along these things. And so these things allow you to go much faster. You can hop much faster. This is well known in physics, like a factor of 10 than a classical discretization. And they're much more stable. And so this is all understood. This has been like 150 years. There's big, beautiful Springer books about this, and it's a beautiful area of mathematics. It also ties directly Hamilton-Jacobi. Those names may be familiar for other reasons. Hamilton-Jacobi-Bellman equations. That's the source of the theory of reinforcement learning. And these equations are at the root of reinforcement learning. Okay, so I remembered some of this, and at some point kind of clicked. I think I was giving a talk at Princeton. Oh yeah, that's right, symplectic integration. Okay, so I'm going to tell you that symplectic integration does work here. And it's not exactly Nesterov, and that's kind of getting back to Nadi's question, that Nesterov is in some sense blending a gradient method and a momentum method. All right, but let's proceed along. I've now trying to tell you what we did. So we did find a discretization which worked. And here's the original equation that had a z and an x. And what we're doing is a variable augmentation where we're putting in a y as well here. All right, and so we get 3 equations out of the 2. And we asked that this y satisfy a certain condition. And here is the condition. If you're familiar with sort of Nesterov style stuff, this is not surprising. Kind of a dual norm on the gradient. This is kind of a relative size of this inner product relative to its dual norm of its gradient. So if y were to satisfy that sufficient condition, then we have a theorem that says that this discretization actually achieves the fast rate in discrete time. So it's stable. And it achieves the 1 over k to the p, not p to the minus 1, the slow rate. Okay? And this theorem was proved in the original paper with Aisha and Andre, and then Aisha has subsequently developed a whole technology of taking a continuous time Lyapunov function and turning it into a discrete time Lyapunov function. So bypassing estimate sequences altogether and just working with the Lyapunov theory both in continuous and discrete time. So she's able in the new theory to kind of get this theorem in a much more slick way and do that for a bunch of other problems. Okay, so that is a discretization, but now how do we achieve this sufficient condition? And again, if you know the kind of Nesterov literature, you know how to do that. You run the primal algorithm. So you interlace that step that we had before from Euler discretization with this step we had from Euler discretization with this thing, which is just kind of the proximal algorithm based on your approximation to f and a regularizer. Okay, so this thing here, if you just ran it all by itself, would have the slow rate. Okay, but when you nest it inside these two steps, this thing achieves that sufficient condition we had on the previous page. So the three equations together give you the fast rate. So people have kind of noticed this. There's some papers on kind of the syntax of Nesterov's method. There kind of be a nesting of a kind of a convex combination and a mirror descent method and a prox method. But that's just syntax. That's not explanatory. And so, you can think about this now as a discretization method, and you can start to discretize these equations in general with this approach. Right? So I've just written it down for the setting where we're looking at these different values of p, but in general, you can use this framework.
Where does Newton's, so you're saying that for higher p's you get Newton's method, but
no, I'm not saying for higher p's you get Newton's method.
get acceleration.
Oh, no, you get cubic constraint, regularized Newton, not Newton's method.
But it's still, does it use Hessian information? Because you're only
Yeah, no, you have to, so to get 1 over t to the cubed, which we can get, and then 1 over k cubed, we obviously are beating the oracle rate.
Right. But where does the Hessian of f
Because we are using f of p minus 1 is the higher order approximation f. So we're making more assumptions. We're assuming that f is not just smooth, but it has the gradient is smooth, or the Hessian is smooth. We're going up this hierarchy of smoothness. As you make more assumptions, you can get faster rates in the oracle rate, and we're achieving that oracle rate.
But you're still using the same first order oracle. You're just
No. We're allowing ourselves now to have. We're doing cubic regularized Newton, for example. So the oracle allows you to have access to higher derivatives.
Is it clear where it comes up with the equation? Because the equation doesn't involve the gradient of f. The dynamic.
Yeah, it does. It involves, this is the Taylor expansion up to order p minus 1 of the function.
Thanks.
Yeah.
Sorry.
No. Okay, so just summarizing what we've done so far is that we have taken kind of where the literature has been in discrete time, which, classically we got algorithms which had this slow rate, but they were natural algorithms. And we didn't do this, but this is known that you can think about them in continuous time. They are gradient flows, and there's kind of a general form of gradient flow where you take the gradient and you normalize it by a particular dual norm, and you can get these rates where p gets larger and larger and larger, but these are the slow rates. And then what Nesterov has done is to move us over to this part of the diagram here. He showed how to take gradient-based methods and accelerate them and get this to be p, not p to the minus 1. And what we've done is to say that, well, underlying the Nesterov approach in continuous time, there's also a way of thinking about this in generality, and it's this Lagrangian approach. All right, so we get the fast rates in continuous time, slow rates, fast, slow. Okay, so that's where we are so far. And now let's return to this symplectic integration idea. Somehow this is all about integration and how to integrate in a quick way. So let's talk about that. So let's just look at gradient flow for a minute. Here's the gradient flow equation. If you initialize close enough to the optimum, this is a good algorithm. But if you're far from the optimum, gradient flow is too slow. So how do you fix that? Well, there are physical systems that we've just shown in the previous part of the talk that take a Lagrangian, and they write this out as a pair of first-order equations, and they can get quicker into the neighborhood. Right? But once you're in the neighborhood, all this momentum they're building up, it hurts you because it makes you oscillate too much, and you don't converge into the answer like gradient flow does. All right, so let's see this. This is just integrating the differential equations. This is doing it with a symplectic integrator, and you can sort of see that it takes kind of big steps, and there's a lot of oscillation that is slowing you down as you start to get towards the optimum. Okay, so the interesting question, I think, is to put these two together. All right, so if you just do that, you just kind of glue the two together, add them together literally, the momentum things we've been looking at so far, if you symplectically integrate them, they're nice and stable. They look, they meet kind of here's the worst case rate. But if you add the gradient thing in, you get an algorithm which also has the same worst case rate, but in practice is actually going faster. Okay, so it's important to note that this discretization is really important. If you turn the step size up too much, this thing becomes unstable. If you have too small of a step size, of course, you slow yourself down quite a bit, especially early on. and you want to be able to use large step sizes. Okay, so to do this, we want to move from a Lagrangian formulation to a Hamiltonian formulation. And this is just because we know that the physicists tell us this is the better way to get actual differential equation solvers that can move quickly and have more robust, stable properties. You take these two variables here, the position and the velocity. You do a Differential transform on the velocity to go to get the momentum, literally just the usual Differential transform you're used to. It's called a Legendre transform in physics, and that gives you Q and P. Now these are non-homogeneous, and that's fine for Lagrangians, that they're time varying. Nothing changes. It's just this total derivative. But when you go to the Hamiltonian formulation, time varying Hamiltonians are not typical. You want the Hamiltonian to be fixed, and you get limit cycles. But there's a way to handle that, which is that you introduce now an explicit time variable, and its conjugate is the energy. So you take this time variable, put it in as an explicit variable in your phase space, you conjugate it, and you get the energy. So now you get these 4 values to define your phase space. And your dynamics now goes from these pair of derivatives to this set of derivatives. These are the classical Hamiltonians, and these are the 2 new derivatives you get to complete the system and get yourself a total constant Lagrangian defined on a well-defined phase space. Yeah?
What exactly do you mean by conjugacy?
Differential conjugacy. Yeah. Yeah, for time and energy. That's right. Okay, so I did not write down the Hamiltonian here, but I can just say it. It's the Bregman divergence plus the F, okay, instead of minus. Okay, the Bregman divergence, the arguments change a little bit too, but basically it's just like in physics, you go from minus to plus. All right, and now with the Hamiltonian, usually you just write down Hamilton's equation, the derivative of the Hamiltonian with respect to P, derivative of the Hamiltonian with respect to Q, set them equal to 0 and solve. We're also adding the T and the energy as well. Long story short though, you can get out the same differential equations we've been getting out with the Hamiltonian perspective as you get with the Lagrangian, but now the integration methodology is different. You can pick up the book, my favorite book is by Harrer et al. It's called Geometric Functional Analysis, is that the word? I forget the word. Anyway, you can take this Hamiltonian now and throw it into that machinery of symplectic integration, and you get these fast algorithms. So here is a step size of 1.125 on a particular problem. This is kind of a banana shape. Here's the Lagrangian integrator. Boom, it goes off to infinity. That's too big of a step size for it. With that same step size, we get a very, very stable, beautiful symplectic integrator. Okay, so if you now add in, you take that symplectic integrator and you add in gradient descent, you get an algorithm, okay? It's now currently motivated sort of ad hoc. We're just taking 2 things and we're putting them together. But we do get an algorithm here, which is this thing right here, which is beating Nesterov, okay? So it's basically the same. It looks different from Nesterov. There's similarities. It's not the same exact algorithm, but it has captured the spirit of Nesterov, okay? Which is that it's able to make fast progress early on, and then it's also later on able to dive into the optimum. Okay, so I'm going to stop here. We're still kind of working on this. Early on, I thought that the following statement was true. Nesterov is just symplectic integration. Okay, and I thought that's a nice discovery. That's not true. Nesterov is somehow a little more sophisticated. It does this convex combination, which is not dynamics. It's kind of a rotation. But Nesterov is, it seems like, symplectic integration plus gradient flow, gradient descent. All right, and so we're still kind of trying to grope towards a principled way of thinking about that. Okay, so that's all I wanted to say about that. Are there questions about that? I've used 45 of my minutes. Yeah.
Can you recover also some rates for non-convex?
No, I mean, we can in principle. We haven't worked on it. So yeah, this framework can absolutely apply to non-convex. You can write down that Bregman Lagrangian, and it will give rates with Lyapunov. But we haven't been working on that. So there's several things we haven't been working on yet. So I kind of wanted to front load this in the talk because this is just starting. We haven't worked on non-convex. We have also worked on stochastic. So it's all about just gradient descent and accelerated gradient. So it's of great interest to talk about diffusions. So take the stochastic stuff and turn it into differential equations and talk about SDEs. And is there an optimal way to diffuse? Is a question you could ask, right? And there's going to be some kind of a Fokker-Planck equation or something like that, or a potential theory equation, which will generate SDEs which diffuse optimally. And so I'm sure that exists. I'm sure there's a parallel theory. And we're working on that too. But and I just want to invite anyone in the room to work on that. I think that there's a lot of you already contributed to things like that. And I think there's a lot of interest in starting to get a more general SDE kind of perspective here. Let me just also note that, before I forget, that symplectic integrators have come up in one other place in our literature and statistics, which is that they are used in what's called hybrid Monte Carlo. So Hamiltonian Monte Carlo, you take Monte Carlo and you write down a Hamiltonian, which gives you the momentum, and then you have to integrate that Hamiltonian. And if you just integrate it in a naive way, it's not that great. If you integrate with symplectic integrator, the leapfrog integrator is an example of a symplectic integrator, then it's much better. And that is the best method, as far as I'm aware, by far in Markov chain Monte Carlo. So it has come up there for kind of a good reason, which is that it's able to make very, very fast progress. And in the MCMC case, towards the optimum, and then still kind of move around stochastically. In the optimization case, we're also seeing it gets you close to the optimum, and then we'd like to dive into the optimum at that point. But there's obviously some parallels here. So integration is behind optimization as well as behind Bayesian inference. Is kind of the message. Yeah.
Yeah. So I don't know if you have time to answer this, but I'm still not quite understand answer the right question. So I see how the gradient descent combines with acceleration.
Yeah.
But in terms of the path itself, right, there's this accelerated path that you got by choosing a specific, tying up all these parameters in a specific way with a single parameter p that actually doesn't matter for the path. That's right, doesn't matter for the path. If you tied those parameters in different ways, you could have gotten gradient flow, or you could have gotten other things.
Yeah, that's right.
If you didn't know,
you would have lost the fast rate. So we were using that as our guide for how to tie them.
Is there a way to think about how to? I mean, it seemed to me, and maybe you can explain this, that you tied these things in a way knowing what the answer should be. If I didn't know about Nesterov acceleration and I had those 4 parameters, and I tried to understand the space of possible things and solve the variational problem of what is the best thing to do, what would even guide me? Because as you said, I can't see from the path itself.
You're asking all the right exact questions that you've been asking, and so the early decision was that these things should be tied to get the fast rate and continuous time. Everything should flow from that, and everything sort of flowed from that, but didn't quite. We got these nice symplectic integrators. They did really well, except Nesterov would beat us at the end. So we've glued on, but you're right, that space we have now not explored. The alphas, beta, and gammas gives us a richer space. We thought this part of the space was the only important part, but it's a richer part, and we could recover other algorithms by exploring that. And now we're motivated to, because we realized that part of the space was very interesting for the first part of optimization, but not for the end. All right, let me move, quick.
So your rates don't depend on H, right?
The rates don't depend on H, that's right. The numbers, the constants certainly do.
In practice,
yeah.
you find that there's...
It's just our usual argument between mirror descent and gradient, It's really, I think of it more as a modeling issue, that it's the geometry that you want to be on, so it's kind of apples and oranges. Okay, let me talk about this second part. I think I've got 10 minutes, and so I'm going to do 5 minutes on each of 2 little topics. These are unrelated to what we've talked about, but I wanted in this crowd to kind of mention ongoing work in my group. So Chi Jen is maybe here, but he's around, and then a bunch of other collaborators spread around the world. So this is about avoiding saddle points and doing it efficiently. Efficient here means getting good dimension dependence. Okay, so we really got to worry about dimension in this particular line of work. This is still gradient descent, and we're going to make some assumptions so that we can talk about avoiding saddle points. Okay, so is avoiding saddle points important? Well, yeah, it's, I remember when I originally was running neural network simulators back early 90s, I got Dave Rummelhart's original backprop code, and I was working with it on a bunch of problems. And I remember how it would come down real fast, and then it would plateau. And then it would come down fast, and it would plateau. And it'd do that like 3 times and arrive at the optimum. And the optimum was really quite impressive. I just remember this to this day. And I think people are still seeing that. And what those plateaus are saddle points. All right, so it's spending a fair amount of time near a saddle point, but if it spent too much time near a saddle point, then you would think you're converged. Right? So it's really important not to spend too much time near the saddle points. So on the optimization side, that's really important. And of course, outside of neural nets, there's a bunch of other problems. Tensor completion is the most studied one, where it's kind of clear there's a global, it's known there's a global optimum, and there's kind of a ring of saddle points around it. And the whole problem is to get past them quickly and get to the global optimum. Okay, so to set up some structure to talk about that, the usual assumption is that for gradient descent is that you just have a first order stationary point, and the usual gradient rate is that there's kind of a Lipschitz constant, and it goes as 1 over epsilon squared iterations in the non-convex setting. So the number of iterations for gradient descent is dimension-free, and that we all know. That's the beautiful fact about gradient descent, which is the main reason, in some sense, that motivates us to pursue it for all of our high-dimensional problems. It's independent of dimensionality. All right, so in general, we have local mins, maxes, and we have saddle points. So we're going to analyze an algorithm which is nearly gradient descent. So if to avoid saddle points, one way to do it is to actually allow yourself a Hessian everywhere. If you have a Hessian everywhere, you can see all the directions of curvature, and you can move out of a saddle point easily, okay, algorithmically easily. But that requires a Hessian. Is it possible you can still move past the gradients, the saddle points quickly, even if you're just using gradients? That's this line of work. So we're analyzing a very simple situation where we're just doing gradient descent, but occasionally we allow ourselves a perturbation which is uniform in some ball of radius r. And we're going to then talk about the theory of how to pick r and ask how fast can perturbed gradient descent with this one stochastic perturbation, which is done occasionally as a function of the norm of the gradient. I'll talk about that in a second. Okay, so to analyze this, we need to have what the optimization literature does is to add a little bit more conditions. There's a notion of a secondary station point where you have the same conditions before, but you also have that the minimum eigenvalue of the Hessian is not too negative. And that you also make a smoothness assumption on the Hessian. If you didn't have that, the Hessian could vary widely over a neighborhood. You just have no hope. So the Hessian is assumed to move in a Lipschitz way around the neighborhood. All right, and we have a theorem which says that this perturbed gradient descent does converge. It converges to these secondary stationary points, so it misses the saddle points. All right. And it does so in a number of iterations, which is, again, 1 over epsilon squared. So it goes as fast as gradient descent, despite there being saddle points. Okay? That tilde there hides dimension dependence, and it turns out that that dimension dependence is polylogarithmic. All right, so I'm going to summarize that on this slide here. So there is an existing set of work that just looks at gradient oracles, an existing set that looks at Hessian oracles, and an existing interesting set that looks somehow in between. Allows you to have your oracle tell you a Hessian vector product, but not a full Hessian. Okay, and so existing work by the same kind of collection of authors was able to show that this convergence rate was polylogarithmic in that ratio, but this new work is showing that it's 1 over epsilon squared. So this was not as favorable in terms of epsilon. It wasn't looking like gradient descent. This shows it really is like gradient descent. And this intermediate work here showed that it was 1 over epsilon, and moreover had a seeming polynomial dependence in dimension, which would be a killer. All right, but this work is now showing that it's actually polylogarithmic in dimension, which shows that it's competitive. It's going to work in high dimensions. Is that 4 real? Well, this was a fairly tedious analysis, and that to get that 4 was some work, but that 4 surely could be brought down. I don't know if it's all the way to 1, but it can probably be brought down. I do want to mention this work here of John Ducci's at Stanford, and his colleagues and others have been also getting these rates of 1 over epsilon squared and logarithmic dependence in dimensions, so very similar with this extra oracle. All right, and now there'll be an interesting debate between these two things. This is a little more complicated. For like backpropagation, you can get these things relatively cheaply, or you can numerically difference. That'll add extra errors you would have to analyze and so on. So it'll be an ongoing thing about whether this is real. You can really get this. I suspect the literature might fold back to this because in my experience of 30 years, the literature always goes for the simplest possible thing. And showing that this little perturbation on gradient descent gets past saddle points is perhaps enough motivation. There's a bit of differential geometry in the analysis here. Let me just point you in the paper. There is a little new differential geometry here, that there's analysis of a so-called, we call it a stuck region around a saddle point that generically all saddle points have it, such that if you are in the stuck region with this little perturbation, if it, with some probability, it will get you out of the stuck region, and if you're out with high probability, the flow will get you out completely. The power method will get you out. All right, and we analyze those probabilities, okay, as a function of the geometry. Okay, yeah.
Do you know that gradient descent without any noise doesn't achieve this rate?
We don't know it doesn't. We don't have a lower bound kind of here, but so this is a sufficient condition. This perturbation gets you this. One could analyze other forms of perturbation. One can analyze no perturbation at all, but we don't know that currently it doesn't. I do not believe it does, but because this argument is generic, and gradient descent I think will generically get in there, but it's not in the proof. Yeah.
There's this sort of like folk wisdom in non-convex optimization or deep learning that the S in SGD helps, and this would seem to add sort of...
It supports to that. This is related. I mean, so we're not doing the S in SGD, which would have stochasticity naturally as part of the problem on every step. We're adding it in a particular way. When the gradient gets small, we add it. And we don't add it. Once we've added it, we wait a little while to add it again. So it's a particular analysis that has to do with this geometry. But there is an ongoing, we're working now on the SGD formulation, can just natural SGD, we can achieve the SGD good rate even if there's saddle points, just with native SGD. All right, last couple of minutes, let me just mention some of the work of Liwa's here on stochastically controlled stochastic gradient. So now we are actually going to SGD kind of algorithms, and I hope you all know about this line of work. I think Francis Bach was one of the people who originated, but analyzing this particular kind of loss function, which is a sum over your data and not just a general convex function. You know, Lipschitz and strongly convex conditions or non-strongly convex if mu is equal to 0. And our oracle is just one unit of cost for gradients and for function values, kind of the usual setup. And there's this SVRG algorithm that kind of, Saga is another example of this that you know, have these favorable rates in terms of epsilon, but have that n sitting there. And that's, you know, if n is 1 billion, this is a killer, okay? And so the problem with these algorithms is that, well, let me write down, show you if you don't know SVRG. Here's SVRG. So Johnson and Zhang. So what they do is they do gradient descent here. You take your current gradient and you subtract off something which involves the globally computed gradient calculated every once in a while. So this is one epoch, one iteration with an inner loop here. And what you do is you compute a full gradient over the entire data set. There's where you pay your n cost, right? And then use it as a control. Okay, you then take the perturbation off your gradient off of that as a way to get the variance down, right? So you can prove that this is has a good rate, and so it's using the stochasticity effectively, but controlling it. Okay, but the computational cost is too high because you have to take this gradient every once in a while. So the natural question to ask is, what if you take a stochastic gradient here? So you don't take the entire data set, you take a small subset of the data to use as your reference gradient, and you plug that in here. Well, that'll give you extra, you'll lose some variance control, but you'll get a computational gain. Can you control all of that and still get a fast rate? And the answer is yes. So just reminding you of some of the rates that you get here for general convex and strongly convex. The things we've just been seeing had these fast rates. This is in terms of epsilon, so it turns things around. If you set t equal to this, you get epsilon 1 over t squared. Here you get 1 over square root of t. So there's your rates for classical gradients. And here are rates for the stochastic case. Here's SGD. This is this new algorithm called stochastically controlled stochastic gradient. I'll show it to you on the next slide. It does take this smaller batch size. It is, like SGD, this is the minimum, so eventually this term will not matter. It is also 1 over epsilon squared. Okay? So these other algorithms, so this algorithm gets rid of the n dependence, all right, and still, despite being extra stochastic, achieves the rate, the favorable rate of SGD. Okay, there is a fancier version of this algorithm. I should say on the strongly convex case as well. It achieves the linear convergence of SGD again with this factor going away, and so it's basically the same as SGD. Right, this algorithm here is actually beating the oracle rate. This is actually going away, log n over n. So it's actually going down not 1 over epsilon squared, but 1 over epsilon. Right? And what's happening is that this is actually an average case analysis. It's not a worst case analysis, so it's actually able to beat the oracle. Let me show you what this algorithm is. It's very simple. It takes the SVRG template, and instead of taking the full gradient, it randomly picks the gradient, a batch of data of size b, where b is relatively small. It computes its stochastic gradient based on that, and it uses that as the baseline down here. Moreover, it is important that it uses a random variable here. It takes the number of inner loop iterations to be geometrically distributed with a particular choice of gamma. So that's actually important in the proof and in the algorithm. So you do this geometric number of iterations and do stochastic gradient descent that. So it's a pretty simple template, pretty easy to run on, to parallelize. And so that's what that does. So there's two versions of this thing. One of them just fixes these batch sizes. The other one makes them increase according to a factor. Okay, I think that's what I wanted to say, and I am now done. Yeah.
Could you maybe go back to the 2 slides?
Yeah. Here?
One more. Yeah, so it seems like to get rid of the independence, you need to choose epsilon to be at least 1 over n or smaller. Is that right?
Yeah, and you want to jump in, by the way, Liwa. But yeah, this is an algorithm which is good kind of when epsilon is not, you're not too aggressive with epsilon. So when n is really, really big, think a terabyte, 1 over n is really, really tiny. And being bigger than that for epsilon is very, very natural. All right, so these analyses where epsilon is much, much smaller than 1 over n is just not very interesting. And some of these analyses, that's the regime they focus on. But I consider as a statistician, that's just not the interesting regime. I don't know if you want to add to that. That's good. Yeah.
So, I mean, you're saying this is beats Oracle's average case, but there is, I mean, we have average case Oracle lower bounds here, which are tight by taking a combination of just either stochastic gradient descent or accelerated SVRG.
Yes. Do you want to jump in? We were just talking about this, and yeah.
I guess the main property is that our algorithm doesn't fall into any framework of existing lower bound
In what
analysis.
sense?
In the sense that in almost all existing frameworks, they need somehow the iterate xk to be some Markovian.
No, that's not. So we have an analysis. I think you're familiar. You've seen that we have analysis which is for any just a straightforward Oracle analysis for an average for lower bound for an average case algorithm. So it doesn't. The iterates don't have to be anything. It's just an Oracle lower bound.
But you need somehow oblivious or something like that. But here, since there's underlying Poisson process, so
oblivious towards what? It's just a lower bound. It's just a lower bound number of Oracle accesses. It's information theoretic lower bound. You don't have any assumption in the algorithm.
Why don't we take this one offline? This is a good discussion. But yes, there's an important question about what do you mean by an Oracle in the average case, and that's yes, Nadia has contributed to that, but there's still some debate. Yeah. Is there anything else? All right. Thank you.